Hi, everybody. Welcome to class today. Today's the last day of the long linear algebra unit that started with the first day of matrices, and we've been doing some applications recently. Well, today we have one last application, one last for us. I mean, there's plenty of applications of matrices, like just one that we're not going to do, but computer graphics are stored in matrices, and when you want to put like a filter, you want to change the color of the picture, that's accomplished through some kind of matrix, like multiplication, causes the filter to happen. So there's so many uses of matrices, but this last one, which I find to be kind of neat, is something called transition matrices. And I'll explain what these are with an instructive example. So here's our scenario. Oh, and by the way, if you have graphing calculator, it will come in handy later on in the lesson. I don't know if you keep it handy, but if you want to have your graphing calculator, I'm going to be displaying mine on the screen, but if you want to follow along with one, feel free to in a little bit. Okay, so here's the scenario. There's a town. There's a lot of variations on this riddle, but this is a pretty easy question. How matrices are involved is less obvious, but here's a numerical question for you. The scenario is there's a town, and there's two barbers in this town, the good barber and the bad barber. And everyone gets a haircut in this town every month. And when you go to the good barber, you get a good haircut, and you next time it's time for a haircut, you're likely to go back to the good barber. But maybe you don't. Maybe some of the people, according to this, 75% of the people who go to the good barber on 1 month will go to that good barber again the next month. So 25% of the people, even though they got a good haircut, they switch to the bad barber, or maybe they didn't get a good haircut. The good barber is not, perfect necessarily. So, but for whatever reason, they switch. 25% of the people who go to the good barber switch to the bad barber the next month. Now, the bad barber is pretty bad, and when someone goes to the bad barber, there is only a 5% chance they will go back to the bad barber, and a 95% chance they'll switch over to the good barber. Now, another assumption for this town is they don't think like more than a month ahead. Like, let's say I went to the bad barber, then I switched to the good barber. The month after that, I still have a 75% chance of sticking with the good barber, and I still have a 25% chance of going back to the bad barber. So there's not like a memory, like, oh, 2 months ago, I'm recalling that bad haircut. No, everyone who goes to the good barber has a 75% chance of staying with the good barber, regardless of their past history. Okay, so here's a scenario now. Let's say that the town has, I'm going to change this. I don't want it to say probability. I would rather this says, actually, that's not the question I want. Okay, so here's the situation. The town has 200 people. And let's say these two barbers, they just showed up. So nobody knows yet who's the good barber and who's the bad barber. So 100 go to the good barber, and the other 100 go to the bad barber. So my question is, what will these numbers change to in the next month? And take a minute to ponder that question, and you could chat about it? How would you calculate it? I'm going to pause the recording while you work on that. Okay, so what turns out to be the numbers on the next month? You can type those in. Oh, fractions of a person, you could just round. Okay, so I see 170 to 30. And the calculation that you end up doing is 0.75 times 100 plus 0.95 times 100. That's the 95% of the people who switch from the bad barber to the good barber. And this is the 75% of the people who stay with the good barber. So that adds up to 170. Well, where have we ever seen an expression like this where you multiply something by something else and a third thing by a fourth thing, and then I add the two answers together? Where have we encountered something like that before? And that's right. I see matrix multiplication. And I'm just going to mute somebody who doesn't realize that they're not. That's okay. And everyone else. Okay, yes, matrix multiplication. The matrix that you would be multiplying would be 0.75, 0.95, 0.25, 0.05. Times the 2x1 matrix, 100, 100. Because look at what happens when you do the actual multiplication. You end up with a 2x1 matrix, and the first element is, yes, 0.75 times 100 plus 0.95 times 100, which is 170. And if I did the other one, it would be 0.25 times 100, which is 25, plus 0.5 times 100, which is 5, added together is 30. So somehow matrix multiplication helps model what's going on here. Now, what if I want to know what's going to happen several months down the road? Because what's going to happen, by the way, you might suspect that eventually everybody's going to go to the good haircutter and there'll be nobody at the bad barber, but that's not how it's going to happen, because there's going to be people switching back and forth. And as I said, people don't have memory of the bad haircut that they had gotten, months before. So what would you type into the calculator if I wanted to know what's going to happen, 3 months from now? What do you think you would do? You could type it into the chat there. Yes, and I see squaring or cubing or doing something like that with the original matrix. So if I were to take 0.75, 0.25, 0.95, 0.05 and stick like a 5 over here, now it would be how many people are getting the haircut, 5 months from now, or I should say, would that be the 6? This is the first haircut would be this when, and this is the second haircut when that's a 1. So this is the second haircut when there's 1 here. So if there's a 5 here, this would be the number of people going to each on the 6th haircut. Now I'm going to switch over to the graphing calculator. And I've programmed in matrix A, but what I didn't do, well here, if I do second matrix B maybe, let's see. Okay, so matrix B is this, and if I were to calculate second matrix B raised to the 5th power, and then I were to multiply that by the starting state, which I go alpha, zoom, I'll make a 2 by 1 matrix, and I'll put 100. And when I put enter, I see that it's 158 and 41. So it's actually less people going to the good barber than the 170/30 situation. And if I come here and I change that exponent to something, even larger, let's say I make it 50. Well, it's not that different than it was when it was just 5. So it's seeming to like stabilize. And that's the first like thing I wanted to show you. Now, we did all that. Got the transition matrix. Talked about that. But now you might wonder, let me go back to the iPad. Is there a way to calculate out the equilibrium point without, you could put a big number into the calculator and see what happens, but there's actually a really easy way to calculate out the equilibrium point. And it goes like this. So some people went to one, some people went to the other. I don't know how many. What do you think needs to go on the right-hand side of this equal sign? What do you think I should put into the right-hand side there? Well, if it actually is at the, if this x and 200 minus x is the equilibrium point, what does it mean to be an equilibrium point? That's right. On this side, you would have, so the equilibrium point is the x and 200 minus x, that when I run it through the transition matrix, it stays the same. Now this looks pretty complicated, but actually it's going to be pretty easy because all I need to do is calculate out, is make an equation out of the first element, either one. So it becomes, if I actually did multiply this thing out, this element here would be 0.75x, that's this times this, plus 0.95 times 200 minus x, which turns into it turns into 0.75 minus 0.2x plus 190. That guy down there doesn't matter because now I can equate the x and this together. That's a minus. So minus 0.2x plus 190 is equal to x. Add 0.2x to both sides. Let me move all the way up here. 1.2x equals 190. And x is 190 divided by 1.2, which is 158, 158 and a third. And that's the equilibrium point. So 158 people going to the good barber. I suppose a third, you could let the good barber do like a third of your haircut and then have the bad barber do 2/3 of your haircut. Anyway, that's our first, that's really the big instructive example. And when I give a test, this is often like the question, the good barber, bad barber situation. What if you end up not satisfied with the first cut and the fraction is yes? So you can, you have two haircuts, or you go and you get multiple haircuts from the same person, like get two from one guy and one from the other. That would be like, okay, more stuff about this now. Okay, we talked about that. Ah, yes. We could also do some stuff with this matrix. Even without multiplying it by something. Like if I just take this matrix on its own and I raise it to the second power. When I do that, it becomes 0.8, 0.76, 0.2, and 0.24. Okay, think for a minute. What does this 0.76 represent now? I like that question. Take a minute to ponder that. All I did was square the transition matrix. I didn't like multiply it by like what's known as the initial state. Because when I had the 100-100, that 100-100 was the initial state. This isn't mentioning an initial state. It's just squaring the transition matrix. Anyone have a thought about what this 0.76, like, what is that the answer to? What question, like Jeopardy, what question is 0.76 the answer to with regard to this scenario? Well, yes, it is related to how many people. So 24, yes, this is even better. The probability that that somebody who starts at the good bad barber will be with the good barber 2 haircuts from now. So maybe they stayed with the good barber and then switched to maybe they stayed with the bad barber and then switched to the good barber, or maybe they switched to the good barber and stayed with the good barber. But this number here represents, for people who get a haircut with a bad barber, because of this 2 here, this is the percent of those people who will be with the good barber 2 haircuts from now, saying nothing about what they did in the last haircut. 76, and someone said them leaving, yes, it's 76% of the people, but they may not leave that time. They may have stayed and then left, or they might have left. It includes all of that. Very often, initial states when there is something multiplied here, it's done not with like 100, 100, but like 0.5, 0.5, like two numbers that like add up to 100%. That sometimes is what goes over here like that. Okay, let's look at another scenario. Did all this. Oh, and I don't even think, did I post the homework? Did anyone know, did I post it? It has like a worksheet and everything. Anyone recall? Okay, I did. So I got like a textbook on this type of math that had like a bunch of scenarios. Sometimes they're really contrived. This is a kind of contrived scenario, but it's interesting. It reminds me of like quantum physics. Here's the situation. There is a particle, and it moves. It can be in one of three locations: location 1, 2, or 3. And it can't be between two of the locations. It has to be, it jumps like a quantum leap from 1 to 2 to 3 or whatever. Here's the story though with this particle. If the particle is at position 1, it has a 50% chance at jumping to position 2 and a 50% chance of staying exactly where it is. It has no chance of going to position 3, at least in like one time unit. Same thing with 3. If it's at 3, it could jump to 2 with a 50% likelihood, or it could stay at position 3 with a 50% likelihood, but there's no chance of it jumping from 3 to 1. And for particle 2, it has a 1/3 chance of staying where it is, a 1/3 chance of jumping to position 3, and a 1/3 chance of jumping to position 1. So that's like the scenario. And as you might speculate, the transition matrix looks like this. Now, with this matrix, I could do a few things. One thing I can do with this matrix is just raise it to a power. So here I'm back to my graphing calculator, and second matrix, well, there's only one 3x3 matrix, so that's likely it. Okay, and that's the 3x3 matrix with this. If I raise this to like the 5th power, and it's probably fun to just say math enter enter also, math enter enter, so we can see that it all as fractions. So those numbers are representing, I raise it to the 5th power, so like 5 movements from now, if I'm at position 1, there's a 781 over 2592 chance that I'm still at position 1. Maybe I stayed for all the times. Maybe I moved to the right, and then to the right again, and then to the left, and then to the left. There's different ways that I could get there, but that's the chances that I am in that position after that many movements. Another thing I can do is I can take that matrix, raise it to a power, and multiply it by an initial state. An initial state, I'll go alpha zoom. The initial state is going to be a 3x1 matrix. And this part gets a little confusing, like what goes inside of this matrix. What I like to do, I mean, you could put any numbers that add up to 1, but what I like to do is usually put a 1 in one of the places and 0 in the other places. This is saying, this is going to give me the answer that if the particle is at position 2 right now, this is going to show me what the chances are. Here, I'll hit enter. That's the probability that it will either be in position 1, still in position 2, or move to position 3. Now, you could put 3 numbers, like different numbers. That's kind of hard to describe. That's like saying, you know, if the particle has a 1/3 chance of being in this one, and a, you know, 1/2 chance of being in this one, and a 1/6 chance of being in this one. So usually my initial state is something like with a 1 saying, yes, the particle is 100% chance it is in position 2 right now, and then it's being run through. But those 3 numbers, you can see those 3 numbers are just an individual row, or sorry, that's just one of the columns. This, maybe I don't want to see the, will that be better? What happened there? Answer to the 5th power. Oh, not answer to the 5th power. I have to do second matrix A. Take that one to the 5th power. I'll just go like this. And you can see that that middle row, column, sorry, is what that other one picked off. Okay, let me go back to the iPad. There's actually only 4 more lessons after today. So after the 4 lessons, I'll do some, like, we'll do test 6, and there's going to be some kind of a delta math. Ethan's happy about that. Ethan got a haircut. Did you go to the good barber or the bad barber? Or you went to your family member? Or you did it yourself? So let's look at another scenario. I only have 3 scenarios for today. This type, if you're interested, if you're finding this interesting, like probability, actually I think I have 2 scenarios left, but this is sometimes called Markov chains. That's sometimes what this is called also. Okay, so here there are 2 gamblers playing against each other. And they're playing a game where A is better than B at the game. So he has a 3/4 chance at winning. And each time someone wins, one person gains $1, the other person loses $1. And the game could go on for a while, because they're going to stop when somebody's out of money. So when someone achieves $5, they're going to stop playing. And the question is, what's the probability that A will be the one who wins after exactly 4 games? So I'm going to make a list of how much money A has. 0, 1. That's how much A has before the game happens. Why is this matrix going to have a lot of zeros in it? You can type in to the chat. Why should I expect this matrix to have many zeros? Oh, I see. I wasn't looking at the chat. We got the answer to Ethan's haircut. I don't think it's a bad barber. Now, there's going to be a lot of zeros here because it's impossible to jump more than $1 at a time. So my first element I'm going to put in is here. If person A has $1 and they lose, they're going to be down to $0. But there's going to be a 0 here because his score must change each time. And there's going to be a 3/4 here. And these are zeros because there's no way to get to $5. So this pattern kind of continues. But something interesting is going to happen over here. It's actually a little bit confusing because, you know, in theory, the game can go on back and forth, you know, a lot of times. But I'm going to do something interesting here. What do you think I should put into this bottom right-hand corner? Yes, and that's right. Why should we put a 1 there? Because you're right about the 1. Why a 1? Yeah, the sum of the columns should be 1. That's true. But there's more of a logical reason why it has to be 1, like based on what the situation is. Yes, once it's over. They don't keep playing. The other guy's out of money. And that's why there's going to be a 1 here also. Because if he goes down to $0, it's going to be over. So now I'm going to take this thing and I'm going to raise it. I always have to be careful about, like, do I raise to the 4th power or the 3rd power? This is the probability. So these numbers are the chance of him being at one of these values after one game. So I am going to put a 4 there. And then I'm going to look at this element over here because he's currently has $3. So I'm going to look at that element over there. I could also, I'm not going to, but I could also do this 0, 0, 0, 1, 0, 0. I could multiply that. All that ends up doing is picking off this column anyway, so I'm not even going to do that. So let me go back over to the graphing calculator. And for this one, I, ahead of time, put in all my matrices. I hope I have them correct. Let's take a look. Well, this one has to be a 6x6 one. Let me just make sure. And it's good to say math, enter, enter, because that makes it fractions. They don't take as much room. Okay, there you go. So now I raise that to the 4th power. I'll say math, enter, enter again. And we can see, well, I was looking for the 4th column, which is the 1/64th, that thing. Scroll down, and you see this 99 over 128. So 99 over 128, which I think is about 77%, which is the answer to this question. Okay, let me switch back to the iPad. Okay, we did that one. Talked about that. Oh, and here's one. So here there's 2 teams. Let's just say, you know, the Mets and the Yankees are playing in the World Series. And the Yankees, let's say, are better than the Mets, so they have a 60% chance of winning any particular game, let's just say. So here's the Yankees. Well, here's how many wins they have. Yankee wins before, and the column is this one's going to be after. So you see there's a 0.4 here because they have a 0.4 chance of losing game. They have no wins, and they'll still have no wins. So this thing is not the Mets wins, the 0, 1, 2, 3, 4 there. That's how many wins the Yankees have after. And you can see in this one, we just have this column of 0.6s and 0.4s. Now, this thing actually goes on infinitely. No, it doesn't. The most there could be is 7 games. So you should probably have 4, 5, 6, 7. But the only problem with that is that it doesn't take into account that once the team wins 4 games, then it's over. We could, yes, it actually could happen. If I put a 1 here, they have 4 games. They're not going to keep playing. That would work. Actually, that would be pretty interesting. So this thing would be kind of complicated. The 5 here is kind of weird because you actually would never get to 5 games. So I'm not quite sure what you would put there. So I didn't think this out fully. I just wanted to show you that like we could do like almost like Bernoulli probability questions, where you want to know if the chances of this happening are 0.4 and the chances of that happening are 0.6. What's the chance that you'll have exactly this many wins in this many, in this many times, this many games? So it's kind of like, remember from last semester, Bernoulli trials? They could be models with the graphing calculus, with the matrices also. Okay, well, that's what I wanted to show you today. Some of these scenarios you see on the homework assignment, it gets pretty confusing, some of these scenarios, but if you have interest in this, it is kind of neat. I've seen like analysis of like Monopoly, like what's the chance of landing on Park Place, if here's, the dice, and there's things like that. And what this does is this actually ends the linear algebra. This was a long unit. It was like 4 weeks worth. It spanned 2 tests. There are 4 lessons left: Friday, Monday, Tuesday, and next Thursday. And then from then on, there's going to be some review. I might make some Kahoot games and have review for some kind of a final, but I don't think it's going to be a final like a pressure that you have to get 100 on at final, more like a delta math that you just do so that you get as many times as you want to get the answer right. Okay, so let me pause the recording.